Hey guys, welcome back. You're here with Miss Gray, and it's time for AP Chemistry. Today we're going to look at the collision theory in podcast 12.3. This is a part of our unit on kinetics of reaction. So we're going to talk about how reactions occur and how fast they go, because that's what kinetics is about. So collision theory says that given enough kinetic energy, atoms and molecules, or ions, will react to form products when they collide. Right? They have to smack into each other first before they can react. And of course, if we have the wrong amount of kinetic energy, the particles will bounce back without reacting. So if we have not enough, and even if we have too much, then they won't react. Collision theory states that in order for a chemical reaction to occur, then the reactant atoms or molecules must first collide with each other. So that's what the collision theory is all about. Remember, laws explain what happens. Theories are our attempts to explain why things happen. So this is our attempt to explain why reactions occur. An effective collision is one in which molecules approach each other. The valence electrons from one molecule will, of course, repel the valence electrons from the other molecule and distort the bonds that already exist in each of them. So if the reactant molecules collide with sufficient energy and also collide in the correct orientation, then the repulsion between valence electrons will break the existing bonds between the molecules and allow new, lower energy bonds to form. Then we get a reaction. So here's an example of a reaction between nitrogen monoxide and ozone, O3. So where we have nitrogen monoxide colliding with ozone, then we get this complex when just at that instant of collision, they are all stuck together. And if this happens just right, these two oxygen atoms will break away as an O2 molecule, leaving the NO2 molecule behind. So we break existing bonds and form new bonds with lower energy. An ineffective collision, though, would not result in a reaction. If the reactant molecules do not collide with the right amount of energy, or they collide in the wrong orientation, then existing bonds are not broken and no reaction occurs. So here's an example of that same collision, only now instead of colliding with a nitrogen atom, the ozones collided with the oxygen side of the NO molecule. And what happens then? They just go back to the way they were before. No reaction, no net change. Let's see another example of that.
For simple reactions, for example those between atoms, the frequency factor A in the Arrhenius equation can be equated with the frequency of collisions between reacting species. However, for more complex reactions, the orientation factor must also be considered. More specifically, how are reacting molecules oriented relative to each other when they collide? The carefully studied reaction between potassium atoms and metal iodide, CH3I, to form potassium iodide, and a metal radical, CH3, illustrates the importance of the orientation of the collision. Click on Correct or Incorrect Orientation of Collision.
Okay, first let's look at the correct orientation.
This reaction is most favorable when the potassium atom collides head-on with the iodine atom in CH3I. Otherwise, few or no products are formed.
Okay, now let's look at an incorrect orientation.
This reaction is most favorable when the potassium atom collides head-on with the iodine atom in CH3I. In this reaction simulation, the potassium atom collided with one of the hydrogen atoms of CH3I. With this collision orientation, few or no products are formed.
So orientation and energy are both important. Recall that chemical kinetics is the area of chemistry concerned with the speed or rate of reaction. What does this mean for the collision theory? That means in all the factors that impact reaction rate, we're really looking at factors that increase collisions between molecules or atoms. So the physical state of reactants or phase of the reactants is going to be important because the more reactant molecules can collide, the faster the rate of reaction will be. So which phase is going to generate more collisions between particles? What do you think, the solid, liquid, or gas phase? If you guess gas phase, then you're right, because they have the most kinetic energy and they move around each other the most. Solid atoms are trapped in their location and they can't collide much with one another. Another important factor to consider is the concentration of reactants. When you increase the concentration, you'll get more collisions. And of course, that means a faster rate of reaction. The reaction temperature also has a positive correlation with speed of reaction. So the rate increases when the temperature goes up because we get particles to move faster. Oh, spelling, increasing temperature. There we go. And then finally, the presence of a catalyst can increase the rate, not because it creates more collisions necessarily, but because it can get the reactants oriented correctly, or it provides a new pathway for that activation energy. Let's have a closer look at temperature and rate. In the collision model, of course, we've got to get our molecules to collide. When molecules collide with other appropriate molecules, then our collision is said to be effective, right? Activation energy is the energy required to initiate a chemical reaction. And so there must be a specific amount of energy involved in order for the collisions to occur. The more molecules we can get that have this amount of energy, the faster the reaction is going to be. So again, activation energy is the specific amount of energy that particles must have in order to react. It's also seen as a barrier that reactants must cross in order to be converted into products. And this leads us to the activated complex. This is an arrangement of atoms at the peak of the activation energy barrier. It's also sometimes known as the transition state, but basically it's that moment of collision when you have all of the atoms stuck together. It only exists for a fraction of time, 10 to the minus 13 seconds. But these are what we would consider our new reactants. We get everything connected, and now we can break apart in new and different ways. So the activated complex has a name also known as the transition state. Let's have a look at this specifically on a graph. So in this picture, what you'll see is that we have an initial energy. So here's our starting place, E sub O, and then we have a final amount of energy. We'll call this E sub F. To get our reactants from reactants to products, they first have to go up and increase their energy. Right here at the peak is where we have that transition state, the activated complex. And as the reaction progresses, more and more molecules get over this barrier and turn into products. Let's take a look at this more closely.
When molecules collide, there must be a minimum collision energy for the reaction to occur. Lacking this energy, the molecules remain intact and no change results from the collision. The colliding molecules must have a total kinetic energy equal to or greater than the activation energy. which is the minimum amount of energy required to initiate a chemical reaction. Click on endothermic or exothermic reaction to view an animation of the energy profiles for each of these reactions.
Let's start with an exothermic reaction.
This is an energy profile for nitrogen dioxide, NO2, reacting with carbon monoxide, CO, producing nitrogen monoxide, NO, and carbon dioxide, CO2. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction. As the two molecules approach each other, an attractive force begins to form between one of the oxygens of nitrogen dioxide and the carbon of carbon monoxide, which is indicated by the dashed line. The bond between the nitrogen and oxygen of NO2 begins to weaken, and the bond length increases. When molecules collide, they form an activated complex, which is a temporary species formed by the reactant molecules as a result of the collision before they form product. In this reaction between nitrogen dioxide and carbon monoxide, the activated complex is NO2CO. The activation energy, which is the minimum energy needed to initiate this reaction, is 132 kilojoules per mole. At this point in the reaction, the bond between carbon and oxygen continues to strengthen, and the bond between nitrogen and oxygen continues to weaken. A bond is now formed between carbon and oxygen. The bond between nitrogen and oxygen has broken. The products of this reaction are nitrogen monoxide and carbon dioxide. The products are more stable than the reactants. The products have a lower potential energy. In this type of reaction, heat will be released by the reaction to the surroundings. The heat released by the reaction is 226 kilojoules per mole. This is an exothermic reaction.
Great, so now let's look at an endothermic reaction and see how that
This
looks
is an
different.
energy profile for nitrogen monoxide, NO, reacting with chlorine molecules, Cl2, to produce nitrosyl chloride, NOCl, and chlorine atoms. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction. As the two molecules approach each other, an attractive force begins to form between the nitrogen of nitrogen monoxide and one of the chlorines of the chlorine molecules. This attraction is indicated by the dashed line. The bond between the chlorines begins to weaken, and the bond length increases. When molecules collide, they form an activated complex, a temporary species formed by the reactant molecules as a result of the collision before they form the product. In this reaction between NO and Cl2, the activated complex is nitrile chloride, NoCl2. The activation energy, which is the minimum energy needed to initiate this reaction, is 85 kilojoules per mole. At this point in the reaction, the bond between nitrogen and chlorine continues to strengthen, and the bond between the two chlorines continues to weaken. A bond has now formed between nitrogen and chlorine. The bond between the two chlorines has broken. The products of this reaction are nitrosyl chloride, NoCl, and chlorine atoms. The products are less stable than the reactants. The products have a higher potential energy. In this type of reaction, heat will be absorbed from the surroundings by the reacting mixture. The heat absorbed, or delta H, is 83 kilojoules per mole. This is an endothermic reaction.
Okay, so now that you've seen the energy profile for a reaction, let's look more closely at how we know what that activation energy will be. How high is that obstacle going to be to get from one side of the reaction to the other? Arrhenius is the scientist who did these experiments initially to relate reaction rate to temperature. His idea was that reaction rate should increase with temperature according to the collision theory we believe the same thing to be true, that when we increase the temperature, we increase the number of collisions. And at the higher temperature, more molecules will have the energy that's necessary to get over that activation energy barrier. So the number of collisions with the necessary energy increases when temperature increases. But it also increases exponentially. So real quick, I want you to sketch out what a graph looks like that's increasing exponentially. You know, is it a straight line? Is it like the y equals x squared? What does an exponential graph look like? Do you have it? The rate constant depends on the temperature, because as the temperature increases, that rate constant increases exponentially. So here's our exponential increase that you can see. This line right here rises slowly at first and then gets faster and faster, steeper and steeper slope. And so we say that this function of the rate law versus temperature is proportional to E, Euler's constant, raised to some frequency factor, this slope of this line here. So what do we do with this? The number of collisions that have the required energy can be described by this relationship that we just saw. Z refers to the number of total collisions, which will increase when temperature increases. E is that opposite of natural log, right, Euler's number. Then E sub A is the activation energy, and notice the sign in here. This is minus E sub A. R is your ideal gas constant, and T is temperature in Kelvin. Which ideal gas constant do you suppose would be most appropriate to use when we're dealing with energy? Right, the one with joules in it. So in the activated complex, we say we have prepared molecules for a reaction. Now they're ready to break old bonds and form new bonds. We can describe how many molecules have an energy that's greater than or equal to the activation energy by this equation, where F is just a letter we use to say the fraction. How many molecules, of all the molecules that we have in our beaker, how many of those have sufficient energy to overcome the activation energy barrier? And so that's where the frequency factor comes in. And of course, R refers to the gas constant, 8.314. And I want to clear that right in. And the Arrhenius equation then is simply making use of that frequency factor. So we can relate the rate constant to the frequency factor that's calculated into this constant here, this A. And for any reaction, that frequency factor is going to remain constant. So what do we do with this? When we rearrange this Arrhenius equation, then this allows us to calculate the activation energy for any reaction. We use the reaction data to do this. Here's what we'll do with it. We're going to compare two different temperatures, the same reaction at two different temperatures, and we'll measure the rates at those different temperatures. Then that allows us to come up with a number that will give us the activation energy for any reaction. So let's give it a try. Ready for this? We're going to calculate the activation energy for this reaction, N2O5, breaking apart, decomposing into NO2 and O2. And we know the observed rate constants at two temperatures. So for A, we have 28 degrees Celsius. Let's convert that to Kelvins, please. So what's 25? Did I say 28? That's 25. 25 is 298 kelvins, and the K is our rate constant at that temperature. So I'm going to take the natural log of which K? K1 over K2. All right. So we're going to put the natural log of 3.46 times 10 to the minus 5 per second divided by K2, 1.5 times 10 to the minus third per second. And that's going to be equal to, what else does this say about it? Minus EA. That's what we're trying to solve for. So that's 328.15 minus 1 over 298.15. All right, so now we've got to get this equation rearranged. We know what all the numbers are. We have only one unknown to solve for. So let's, okay, so I have minus E sub A, and on this side, I've got 3.7084 something something, bunch of calculator vomit that I'm not going to bother rounding yet. And then over here, we're going to take the natural log of the first rate divided by the second rate. Oh, whoops. The natural log of 0.0231, and that was negative 3.76, blah, 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 equals my negative E sub A times all this nonsense, negative 3.71 times 10 to the minus 5. Okay, so now let's solve for E sub A. I end up with an activation energy equal to 102.105.0596. What does this mean? I'm going to keep only 3 sig figs, so 102,000 joules. And that's got to be joules per mole. My temperatures canceled out. So remember what your units for R were, joules per mole per Kelvin, right? So that's how we use the Arrhenius equation to get to that activation energy. Great, well that's it for this podcast. I will see you guys in class.